You are given a set of strings and you have to find out the number of pairs I comma j such that if you concatenate the strings at the index I and index j, then the resulting string has at least one permutation, which is a palindrome. In the example that you see on the screen, suppose you pick the index 3 and index 6 and concatenate the strings at these two indexes, then the resulting string would be D, F, F, E, double A, D, E. This resulting concatenation by itself is not a palindrome, but you are allowed to shuffle this or permute this as many times as you want, as long as you can create at least one permutation, which is a palindrome. And you can see that this concatenation is a legit concatenation because the palindrome that you can create, one possible palindrome could be A, E, F, D, D, F, E, A. So you can see that I have just rearranged the characters in the concatenated string to get this palindrome. So this pair is considered as a valid pair, and your goal is to find out how many valid pairs are there in this array with an optimal time complexity. So in this video, we will develop some techniques to solve this hard problem, and after you have learned those techniques, you can see that you can apply those techniques to future code forces problems as well. So before we jump into the solution, let's start with an easy version of the problem first. That is, if you are given a string, if you are given any random strings, let's say a b c a x x b c, and if you are asked to find whether this string itself is a palindrome or not, then you know that the standard algorithm is to have two pointers, one from left and one from right, and as long as the left and right pointers point to identical characters, you keep on moving the pointers forward or backwards depending upon which pointer it is, and at the end you will have an O of n algorithm to compute whether this string by itself is a palindrome or not. Now if I ask you to tell me whether any permutation of this string is a palindrome, can you come up with an algorithm? So you might think about the fact that if you are allowed to do any permutation, it means that you can shuffle each character to any position that you want. So the logical next step is to have, so we know that there are only 26 characters in the English alphabet. So we start with 26 blocks and one block for each character in the alphabet. So we have A, B, C, etc. And this is the last block. And we will maintain something known as the frequency. So it would be easy for maintaining the frequency, because with the frequency array you might lose track of the ordering of the elements, but then the ordering doesn't really matter because this is a permutation. So like let's say you have created the frequency, and let's say the frequency of this is 29. Now just by looking at this frequency array, can you determine if any permutation of this string can be a palindrome or not? So you can realize that if the permutation is indeed a palindrome, then there will be a partition point over here. So suppose this is a partition point, and right now I am assuming that the string is of odd length. So this is the partition point. And every element on the left hand side should also appear on the right hand side, because this partition point acts as the mirror. That is what a palindrome is. So you can see that if an element is appearing here, it should also appear over here at the same distance. Therefore, you can conclude that the frequency of each element has to be even, right? the frequency of each element has to be even except for the partition point, because the partition point itself that you considered, that does not need to be mirrored. For example, in palindromes of length 2 or of length 3, you can see that a is a valid palindrome. So each character has frequency even, but the partition point, the middle point, can have one odd frequency, and that is fine. So you can see that the answer to this problem is, for a given string, you just check the frequency array, you create the frequency array, and the necessary conditions are that frequency of each character frequency of each character is even except at most one odd character. Except at most, it is not necessary that you guaranteed have one odd frequency, because this is also a valid palindrome, uh, a, right? So this is also a valid palindrome of length 4, where frequency of all the characters is even, which is 2. Sorry, the frequency of all the characters is 4. So you are allowed to have a maximum of one odd frequency. That is why I have mentioned except at most one odd frequency. So in this manner, you know that you can maintain the prefix array, you can maintain the frequency array in O of n in just one single pass. So in this manner, given a string, you can quickly answer whether any permutation of this string will be a palindrome or not. All this is fine, but the reason why I started out with this simpler problem is to change your perspective and look at this frequency array in a different format. So right now, let's go to the new page. You can see that right now you are accustomed to seeing the frequency array as a vertical array with frequencies written on it. So you have A, you have B, you have C, and then all the way towards the end you have D, and each element has a frequency written corresponding to it. 5, 9, 3, let's say 21. The first observation that you can make is that since we are only interested in the parity of the frequency, that is whether it is even or odd, then the actual frequency doesn't matter. So we might as well reduce the frequency down to either 0 or 1 depending upon the frequency. So this is an odd frequency, so we'll mention it as 1. We are just taking the modulo 2. So this is an odd frequency, we'll mention it as 1, and let's keep this frequency as even. So this gets transformed to 0. Now what I want you to, so this is the first transformation that we have did. So keep in mind the transformations that we are making. So the first transformation is only the parity matters. Only the parity matters. So you convert each frequency to frequency modulo 2, right? So this will bring it down to a set containing only 0 and 1. So this is the first transformation that we have done. The second transformation that I want you to do is, instead of viewing the characters as just characters in the English alphabet, you can see that in competitive programming, the most common entity that we deal with is integers instead of numbers. So why don't you have indices over here instead of having actual characters? So you replace characters with indices. So there should be a one-to-one mapping, and you should be able to create this one-to-one mapping. How? You can assign an index 0 to this, an index 1 to this, index c to the index 2 to this variable 2, and then an index 25 to the last variable, which is z. So you can see that given any index, so if I give you index 24, you can easily recover which character it represents. Which is it? This is nothing but the character y. So all you have to do is you have to add the ASCII value of a to 24. Basically you go 28, 24 steps forward from the ASCII value of a, which is 0. Now that you have this replacement, and most of you might already be familiar with this replacement, the third and final transformation that I'd like you to do, that instead of visualizing it as a vertical array, because there are only a very few places where you see vertical array, which is the stacks scenario, but most of the time you deal with the horizontal array, right? So you replace the vertical array with the horizontal array. Replace vertical with horizontal array. Now let's see what is the structure that we get after doing this replacement. So once you do the replacement, you will see that you will have an array of length 26, because there are 26 characters in the alphabet, and this is index 0, this is index 1, and this is index 25, because the array is of length 26, and each entry of the array would either be 0 or 1. So let's say this is 1, let's say this is 0, let's say this is 1, 1, 0, so on, and finally this is 1. But now you can see that you have what is essentially a binary string. So if this is a binary string, then you can actually represent this binary string. It must also have a decimal value corresponding to this binary string. So the fourth, not really a transformation, but just a change in perspective, is that from the binary string, you compute the decimal value. Compute the decimal value. So you see that you started out with 26 characters and some frequency. Those were a lot of numbers. So you decided to trim it down to either 0 or 1. But then those were a lot of characters. So you decided to convert it to indices from 0 to 25. But now you have a binary string. But then binary string contains again 26 digits inside of it. So can we compress it down even further? So yes, we can do that by visualizing this big binary string as not just one very big binary string, but a simple decimal value of it. For example, if you had this binary string 101, you could visualize it as 101, or you could also visualize it as 2 to the power 0 into 1 plus 2 to the power 1 into 0 plus 2 to the power 2 into 1, which is nothing but 2 plus, sorry, which is nothing but 1 plus 4, which is equal to 5. So either you can visualize it as 101, which is a binary string of length 3, or you can visualize it as a single number, which is 5. And you can see that there is a one-to-one mapping between them. Why? Because any decimal value will have a unique binary representation, and any unique binary representation will have a unique decimal value associated to it. So now you can see that starting with these many variables like characters, frequencies, and whatnot, we were able to reduce it down to a single number. And this number that you get, that is after converting this frequency array into a 0 1 binary string, and then converting this entire binary string back to a decimal value, this number that you get, that number is called as a bit mask. So you see that bit mask is nothing but a decimal value that behind the scene it incorporates all the metadata of your initial problem, like how much what is the parity of each character. And you can see that the maximum value of this bit mask would be what, 2 to the, so there are 26 bits in total, so the maximum value would be 2 to the power 26 minus 1. And why do I say that? Because you can turn on all the bits in the worst case scenario, means the frequency of all the characters is odd. Once you have this bit mask, what do you do with it? How do you use it to solve the original problem? So remember that a bit mask is now just a decimal value between 0 to 2 to the power 26, where 2 to the power 26 is excluded, right? So closed open range. Now given that same problem again, like given a string, any random string, like let's say a b a r a c e c a r, and then I ask you to tell me whether this string is a palindrome or not, then you know that this string will have a unique frequency array representation. That frequency array will have a unique bit mask associated with it, which will just be a number, let's say num. Then just by looking at this number, what can you tell me about the answer? Can you conclude whether the whether at least one permutation will be a palindrome? Yes, you can do that by checking that the original problem, we had concluded that there should be a maximum of one odd frequency. This means that in this number there should be a maximum of one set bit. So nothing new here, just a change of perspective. And this change of perspective, even though it might seem very trivial in this problem, it will help you a lot for future problems. So this number can have a maximum of one set bit. But what does a number with one set bit look like? So you will have something like 0 0 0 0 0, and there will be only one set bit over here, this. So you can see that this number is nothing but 2 to the power I, where I is the position of the set bit, because there is a one-to-one mapping between binary strings and their decimal value. So this number will create at least one permutation which is a palindrome only if it is equal to 0, means 0 set bits, or if it is equal to a power of 2. So you can see how we were able to modify a very string based problem that dealt with only strings and palindromes to something that deals with the arithmetic world. We can say that this string will have one permutation which is a palindrome if and only if the bit mask corresponding to its frequency parity is a power of 2 or it is 0. Now I'm not saying that this bit mask approach is easier or faster. This is just a different way to look at things. But then the benefit is that you had such a long string, right? The length could be up to 10 to the power 5. So first you reduced it down to a frequency array whose length is only 26. And then you reduced it down even further to just a single integer value. So you can already see the benefit that your brain only now has to process one single integer at a time. And then it can already use some existing functions to figure out whether that integer is a power of 2 or not. So this was a fancy way of solving the easy version of the problem. Now, how do we solve the hard version of the problem where they ask you to figure out whether their concatenation is a palindrome or not? So let's see how does permutation affects, how does the concatenation affects the bit masks that we are creating. So let me copy this string. In this string, you know that each number will have a corresponding bit mask associated with it. Let's look at the bit mask for DFFE. So I will create an array where this is the block for A, this is the block for B, this is the block for C, block for D, block for E, and this is the block for F. So what will the bit mask of this number look like? So the frequency of F is 0, so you write 0 over here, and frequency of D is 1, and frequency of E is also 1, and then the remaining characters are by default 0. So what number does this represent? This is nothing but 2 to the power 3 plus 2 to the power 4, which is nothing but 8 plus 16, which is equal to 24. So the bit mask for this number is 24. Now what does the bit mask for this look like? So let me again create the blocks. So this is the block for A, this is for B, this is for C, this is for D, and this is for E. Frequency of A is 2, which is identical to 0 because we are taking it modulo 2. So this will be 0 over here. Frequency of D is 1 and frequency of E is 1, and this is 0, 0. So you can see that this number's bit mask and this number's bit mask is also same. So this is also 24. Now what happens when you concatenate these two? So if you concatenate these two, you will have two bit masks. Let's write down the bit masks for both of them side by side in top-down fashion. Let me copy this. Okay. And here you can see that suppose the first element had this bit mask, let's say 1 0 1 1 0 1 1 0 1, and the second element had the bit mask 0 1 1 0 0 0 1 1 1. Then you can notice that this is the block for A, this is the block for B, this is the block for C, and so on. So the first string had odd number of A's and the second string also had odd number of A's, but when you combine them, the number of A's would become even, right? Because the total count of odd plus odd will be even. So the bit mask will represent bit mask for the final combined concatenated string will have a 0 at that position. Now let's look at this one. The first string had even number of B's and the second string had odd number of B's. So when you combine them, the final string will still have odd number of B's. So you can still see the relationship that if you have 1 comma 1 means odd comma odd frequency, those are getting converted to 0 because they will now lead to even frequency. And then 1 comma 0 or 0 comma 1, they are getting retained to 1. And of course 0 comma 0 will still be 0. So you can see that each bit is nothing but the bitwise OR. Bitwise OR. So exclusive OR. So this expression is called exclusive OR, which is the bitwise OR. So in fact, you don't really have to go back to the binary representation anymore. You just take the first element, which is the mask 1, and you take the second element, which is mask 2, and then you apply the bitwise XOR operation on them to get the combined mask after their concatenation. So you can say that even though we have not solved the problem, but we have reduced the problem down to set of integers, and our reduced problem is that you are now given a series of masks. So let me write down the problem statement clearly for the reduced version. Given n masks, compute how many pairs such that mask I or mask J is a power of 2, right? Because that is what we wanted, that their concatenation and the concatenation is nothing but the bitwise XOR, which is nothing but the XOR of two integers. And we wanted that concatenation to have at most one set bit, and at most one set bit is nothing but a power of 2 or 0, right? Power of 2 or 0. So this is the problem, and you can see that at least we have gotten rid of the strings altogether. There is no strings in the picture at all. So this is a modified version of the problem. Like, I give you some mask. Every number can represent a mask. Remember that, because there is a one-to-one mapping between a binary representation and a decimal value. So now let's say the problem gave you some masks like 3, 5, 7, 7 and 22, 100, etc. And your goal is to find out how many pairs will combine together in the XOR fashion. How many pairs are there in the array whose bitwise XOR is a power of 2. How do you solve this version of the problem? To do that, in one of these in one of the videos where we talked about the inversion count, you will remember that whenever you have something like some pairs I comma j, then to simplify things, you always think about one pair interacting with its left neighbor instead of viewing it both ways to avoid overcounting. For example, you say that this 22 will always be paired to something on the left hand side, not to something on the right hand side. So for example, uh, you want to ask the question that if the right pair is 22, if j is equal to the index pointing at 22, then how many left pairs are possible? How many i's are possible? So this is one of the contribution techniques that we have also discussed, that every time you are asked to find something over all ij, you fix one endpoint and then you only look towards its left. So assume you are going from left to right and you are at an index j, and you ask the question, okay, if I fix the right endpoint and I already have one mask as a of j, can I find how many masks exist to the left hand side? How many masks are there on the left hand side that can combine with a of j to give me a power of 2? Can I ask this question? Now you will start realizing the power of what we have done via these transformation. So this question is itself hard to solve, because you might want to think about iterating over each of these elements and checking, but how do we solve it efficiently? So you will realize that power of 2's, they are very limited in numbers, because the numbers that we are dealing with, they only have 26 bits. So there can only be 26 different possibilities for the power of 2 that can come from the concatenation of these two, basically the XOR of these two masks. So why don't we try all the powers of 2? Like, we list down all the powers of 2: 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on, up to 2 to the power 25. And then you ask the question, okay, for a given 2 to the power k, how many elements are there such that on the left hand side, how many elements x are there such that x XOR aj is equal to 2 to the power k. Now this problem itself is hard, right? Because there is nothing fancy that we have done. We have just changed this power of 2 to applying a brute force over all the 2 to the power k that are possible. But now you can see that since we are using XORs, and XORs have a very interesting property that you can XOR something to an expression on both sides. So let's go to the new page, and we are here. We are here. XOR AJ is equal to 2 to the power k, and we will vary k from 0 to 26, where 26 is not included. And the pictorial representation was that we are iterating from left to right and we are at this index j. So if you XOR both side by a to the a of j, you will have this expression XOR aj or aj is equal to 2 to the power k XOR aj. And XOR has an interesting property that y XOR y is equal to 0. So you can see that this expression simply reduces down to x is equal to 2 to the power k, which is known to us because we are iterating k, and XOR aj. And this is also known to us, means the right hand side is known to us. So you can see that that very complex problem of finding the bit masks and whatnot, and palindromic pairs and whatnot, has been reduced down to just one simple query. That is, how many elements are there on the left hand side with this particular value z. Let's call this value z. So the question is, how many values, how many elements have you seen on the left hand side whose value is equal to z? And that part you can easily maintain by keeping a map. You keep a map with the frequency count of the elements that you have seen so far. This is a very standard trick. And this way you can solve the problem. The other thing is, how do you, we said that how many pairs are there where the mask is the power of 2 or the mask is 0. So when will the mask be 0? So if x XOR aj is equal to 0, means x is equal to aj. Means all you have to do is find how many elements are there inside your map with the same value as the one that you are currently at. And in this manner, you can see that for each index, we are only doing O of 26 operation, because you have to iterate over all of these 26 possible power of 2, and then we are doing a login lookup in the map. So you can solve the overall entire problem in O of n log n. Finally, let's look at the code for this problem. So for the code, you can see that we are iterating over all these strings first and then converting it to the mask that we talked about. And for converting it to the mask, you can think of any string as starting out with a single element and then concatenating it repeatedly. And we already talked about the fact that if you want to concatenate repeatedly, you can use the XOR operator. And if you want to turn on a certain bit, this is the fancy way to do that. And then once you have a set of numbers, you iterate over each element from left to right, and first you compute the XOR, compute the answer when the bitwise XOR has 0 set bits, means the number after their XOR should be 0. So therefore you are looking at the identical copies of the mask, because target is 0 over here. And once you are done with that, you iterate over all the 2 to the power 26 possibilities, and you figure out your target, which is, this is nothing but 2 to the power I, and you look for aj XOR 2 to the power I in your map, and then you increment your count, because you have seen one mask with this value. So in this manner, we were able to solve the problem in O of n log n. So I hope that this technique of visualizing a string as a mask and then the major benefit of this approach is that you don't have to think about a lot of things at the same time. Now you only have numbers to worry about, and when you have numbers to worry about, and when you talk about x or y is equal to z, you don't necessarily think about bitwise operations all the time, because if I ask you x or x, you can simply say that it is 0, or you can simply say that it is possible to transfer this x on the right hand side. So I hope that this representation will benefit you in future problems. If you have any feedback for me, let me know in the comment section. Thank you.